This is a brief review of the quantum numbers. All right, so here's the table we filled out in class, and I wanted to leave this here in case anybody needed to correct anything on theirs. Additionally, a quick review. So remember, this principal quantum number is the energy level, and it corresponds to the rows of the periodic table. Though these, quote, rows are going to get a little thrown off when we hit the d and f orbitals. This angular quantum number, L, indicates whether or not we are in the S, P, D, or F sublevel. So remember, if it's S, that corresponds to 0, P is 1, D is 2, and F is 3. The magnetic quantum number is slightly more complicated, and I'm going to draw this. Okay, so this I'm going to take all the way down here. If we have an S shell, we know it only contains one orbital, and we would label that as 0. If we have a P sublevel, so L was equal to 1, and we had P, then we know that indicates 1, 2, 3 orbitals. So S has 1 orbital, P has 3, and those will be labeled -1, 0, +1. For D, D has 1, 2, 3, 4, 5, which would be -2, -1, 0, +1, and +2. And then F has 7, so 1, 2, 3, 4, 5, 6, 7, starting with -3, ending with +3, and it looks like this. Keep in mind that these values, these -1s, -2s, +3, whatever the value is, this just describes one of the possible orientations the shape can take. So for example, I'm going to show the example here with a P. We could have the orientation like this, it could be like this, or it could be along this, so the direction like that, straight up, or horizontal. And each of these corresponds to a different orbital. So one of them corresponds to this orbital, one corresponds to this one, like this could correspond to that, and the other would correspond to this third. Not necessarily in that order, but just to give you an idea of what these values mean. It's just a way to represent the different orientations that this shape can take within the orbital. So whether it's along the X, Y, or Z axis. All right. Now, since we know that we can have a maximum of 2 electrons in each of these orbitals, S can hold 2 electrons total. P can hold 6. D can hold 10. F can hold 14. And then finally, if we had to fill in electrons in these, and I'm just going to start here in the D sublevel, we always place one pointing up, so this positive spin, all in the same direction, and then we will start pairing. So it would go 1, 2, 3, 4, 5, and then we can start pairing 6, 7, 8, 9, 10. Keep in mind, we can't actually start putting anything in any kind of d orbital until all of the s and p orbitals before it are filled. There will be some exceptions to this rule later, but don't worry about that right now. Now, I also wanted to go over these questions again in case it didn't make sense the first time. So for this first one, identify the subshell in which electrons with the following quantum numbers are found. If we're looking for the subshell, we don't even care about this n equals value. So this part isn't actually helping us. We can just focus on the L equals and look at the number. Remember, for the subshells, our options are S, P, D, and F. So we know if it's an S, L is equal to 0, which means, in this case, this one has to be S. Since this P is equal to 1, so the first one would have to be P. And then D is equal to 2, so the middle one would have to be D. All right, now this next one. If N equals 7, what are the possible values of L? To figure out all of the possible values, remember it's going to start with 0, and the maximum value it can be is N minus 1. In this case, the maximum value for L would be 6, but it could also be any number below that. So starting with 0, 0, 1, 2, 3, 4, 5, 6. All the way to N minus 1, which in this case is 6. Okay, number 13. If N is equal to 3 and L is equal to 2, what are the possible values of ML? All right, so for this one, we actually don't even need the N equals 3. That isn't going to help us here. What we do need is L. If we know that it's equal to 2, we know we're looking at a sublevel of D. And the D sublevel has 1, 2, 3, 4, 5 orbitals. Remember, each of these gets a value. So -2, -1, 0, +1, +2. So if we want to know the possible values of ML when L is 2, it would simply be all of those values, -2 through +2. And finally, the most complicated one we ran into. Which atom's final electron has the following quantum numbers? Okay, so in this case, we do care about all of them. We need to know what row of the periodic table this element is in. We need to know which sublevel, where in the sublevel, and then whether or not it's going to be the electron pointed up or down. So I know from N equals 2 that this element is going to be in the second row of the periodic table. And if I take a look at those electrons, my options are Li, Be, and then jumping across, B, C, N, O, F, and Ne. Well, I see next that L equals 1, which means I'm in the P sublevel. Li and Be are both in the S sublevel, so I know it can't be these. It has to be one of these 6. So let's take a look at the magnetic quantum number, so ML. We know if L equals 1, we are in sublevel P. Okay, so P. So L equals 1, so P. P has 1, 2, 3, and we know they're labeled -1, 0, +1. Let's say they were completely filled in with electrons. Well, we won't even get to that point yet. So if it's ML equals 0, we know the electron has to be located here. And if it says MS equals -½ it has to be the electron that's pointed down. All right. So if we were doing boron, that would correspond to having 1 electron pointing up. Carbon would have 1 pointing up in this second orbital. Nitrogen would have 1 pointing up in this +1, so it would be 1, 2, 3. These are all pointing up, so we know it can't be any of these elements. We haven't even started using the oppositely spun arrows, these negative arrows. So then for oxygen, we're adding a 4th electron, so it's going to point down. Fluorine, here we are, and then neon fills in the last one. So then we know that this 5th, here I'll highlight it, this electron here corresponded to fluorine, and this was the method I used to determine that. These questions like number 14 are definitely a bit confusing, and you have to think about it, but I hope that as we continue practicing orbital diagrams and electron configurations, it will make more sense.